Right. So the final stretch is the last module and some questions from the previous FAT papers. Artificial neural networks. So principle is they're similar to the brain. They're an information processing model with interconnected units known as neurons. Like humans, they learn by example. Each neuron is connected by a bunch of connecting links. So they also have an activation level, which is their internal state. So this is transmitted to other neurons. This is a basic diagram here. So there is a x1, x2, they are inputs. W1 and W2 are the weights of the links, and Y is the output here. So here, Y in, which is the input going into this Y node, is x1 W1 plus x2 W2, which is the weighted sum of the inputs. And then Y, which is the output here, is a function of the input coming into Y. So a combination of this goes into Y, and then a function of whatever comes in here is the output here. So the entities of ANN are quite simple. The first is interconnections, the second is learning rules, and the third is activation function. The first is connections. There is a single layer feed forward type, which is basically it has one or more neurons all connected. The input layer is the output layer. There are no layers in the middle. So you see all the nodes are connected here. So this is W11. Since this is connecting the X1 and Y2, this will be W12. And similarly, you would go on until level Xn and Ym, how many ever you have. The second is multi-layer feed forward. So you have X and how many ever X nodes, and then you have a bunch of hidden layers in between. Notice that all of these nodes are connected to each other, and then you have the output node as well. This is just a bunch of theory that you need to keep in mind. Single node with its own feedback, obviously just a single node, and then the input is its own output. It comes back as feedback. Single layer recurrent network, where outputs are also considered as an input. So one of the inputs coming into this Y1 is its own output. So Y out becomes an input later. And in multi-layer recurrent, this is basically a combination of multi-layer feed forward and single layer recurrent. Basically, this happens in this. So you just combine the two diagrams. There are two types of learning. The first is parameter, which is updating connecting weights. Second is structural. It's a difference in network structure. The most important thing to note here is activation function. The purpose of an activation function, if they ever ask you, is to introduce non-linearity into the network. So a bunch of types of this. The first is an identity function, which is f of x equals x. The output is always equal to the input. And the second type is a binary step function. So we have f of x is 1 when x is greater than or equal to 0, or theta here. And here is theta is a threshold value that we use instead of 0. And f of x is 0 if x is lesser than that threshold. So let's say threshold is 2, then it's going to be 1 if x is greater than 2, and 0 if not. Third is bipolar step function, which is the same as a binary step function, except you have -1 instead of 0. You use the same threshold. The fourth and most important one, arguably, is the sigmoidal function. This is the one used in back propagation and forward propagation and whatnot. There are two types of this. The first is binary sigmoidal, which is f of x equals 1 by 1 plus e power minus lambda x. So you can ignore lambda for now, but what you need to focus on is the x here, which is the net input. So for now, you can just remember this as 1 by 1 plus e power minus x. And honestly, this property is a bunch of theory. That is, the derivative of this function is lambda f of x times 1 minus f of x. The graph for this bipolar sigmoidal functions, f of x equals 2 by 1 plus e power minus lambda x minus 1. This is also something you can ignore. This derivative property is also something you can probably ignore, but it's useful to have in mind anyways if your prof is like a theory focused prof. The final is a ramp function, quite simple, not much explanation needed. But the one that you're going to see most often is the the sigmoidal binary for back propagation, etc. So an example of this question is find the output of this neuron Y using one binary, two bipolar, like sigmoidal. The first binary sigmoidal is given by 1 by 1 plus e power minus y in. Again, for the bipolar, it is given by this formula. Y is net input into this node, and this is going to be this plus the weighted sum of the others. So this is a random input that we're getting. So 0.35 plus the x1 w1 0.8 times 0.1, 0.6 times 0.3, 0.4 times minus 0.2, and you eventually get my 0.53. So this is the y in that you get. So here, when you input 0.53 into this formula, 1 by 1 plus e power minus 0.53, you get 0.625. This is for the binary sigmoidal. And then for the second one, bipolar sigmoidal, you input into this formula, 2 by 1 plus e power minus 0.53 minus 1, which is 0.259. That is your answer. Back propagation is probably something that's not there, but there is a formula for this. So you repeat the same steps that we just did. So here there's just an extra hidden layer, but that's the same process, right? So you operate on this assuming that the output of the hidden layer is the input of this. So the input of this is the sum of y3 and y4. And those are the outputs of the hidden layer here. And the input of this is the sum of x1 and x2, the weighted sum for both of these anyway. So you do the same thing, you find um, y4, y5. Yeah, so Wi-Fi output is 0.69. So the question says here that the actual output is zero point 0.5. So the error here is zero point 0.5 minus 0.69, which is minus 0.19. So backpropagation works on the principle that you change and update weights based on this formula, which is delta W equals N, I guess. I don't know what this formula is called. I forgot. Um, which is delta J OI. And then for an output unit, you use this formula, which is OJ 1 minus OJ, TJ minus OJ, OJ 1 minus OJ, which, and then a sigma of delta K and WKI. And this is for hidden layers. So this is for the output unit, which is this. This formula is for the hidden layers. So you substitute all of this. You solve for delta 5 first, then you get the rest of the values. Honestly, they won't ask this much, but this is pretty simple math. So if you really want to go through it anyway, then you're welcome to do so. And then you find the updated weight with the formula that we have. And this is the delta weight. Updated weight is old weight plus updated weight delta. So you update all the weights in this network as such. Time to look at some theory again. Convolution neural networks, feed-forward neural networks used to analyze visual images. They process data with grid-like topology. So every image becomes a grid of pixel values with binary zeros or ones. So a simple look at the process of convolution. 532, 597, 123. So the way convolution works is you slide this B matrix over this A matrix. So the first three elements are considered first, and then you multiply each element twice and you add them. So 5 plus 6 plus 6. So it's just 5 into 1, 3 into 2, 2 into 3, 5 plus 6 plus 6, 17. Again, you take the next two, you move one element over, 3 to 5, and then you repeat the same process. You repeat it over and over again. So the next would be 259 and then 597. So you do that 5 times over. That's how the principle of convolution works. So in a CNN, there are four layers. The first is a convolution layer, the second is a ReLU layer, the third is a pooling layer, and the fourth is a fully connected layer. So the first is convolution, which extracts an image feature as a matrix. So you slide this matrix over each. So you take this 3 by 3 matrix, put it on the first 3 by 3 here, then you move it one column over, and then you move it one more column over. So you see that in this part, we have 1, 2, 3. You can place this in three different configurations, and then you get three different elements. So you do convolution for this overlap, and this overlap as well. And then again, you move it one row down, and then you do the same thing. And then you move it one more row down, then you do the same thing. You get 9 elements overall, and you get usually the convolution matrix is using this matrix, but they'll also give you the matrix, so it's nothing to really be concerned about. The second is a ReLU, rectified linear unit. It activates only if your values are greater than a threshold. So this is in charge of eliminating negative values. So if your matrix has any negative values, it uses this function, which is f of x is max of 0 comma x. Basically, if there's a number greater than x, it'll ignore it. If there's a number lesser than 0, greater than 0, it'll ignore it. If there's a number less than 0, then it'll make it 0. So element wise, it does that. So 2 comma 2 comma minus 1 is converted to 2 comma 2 comma 0. Everything else remains the same. Minus 1 is converted to 0. The rest of the values stay the same. So ReLU does that, removes negative values. Pooling reduces size or does downsampling by decreasing the dimension. So this is done by either max pooling, so the max value of pixel from the range is covered by the kernel is taken out, or the average pooling, which returns average for the same range of pixels covered by the kernel. So this is what is known as a kernel, this matrix right here. So we do the same thing that we did here. So here, for example, let's say that we have a 2 by 2 kernel and we put it over the first four here. The maximum is 20. Then you put it over these four, 30. These four, 112. These four, 37. So this is, so sorry, wait, no, you don't do that. 12, 20, 8, 12, 20, 30, 12, 2, because you move it only one cell to the right, and then 30, 0, 2, 0. So it would be 20, 30, 12, 2, and then 34, 70, 112, 100. Wait, no, that doesn't make sense. Hmm. Max is 20, 30, 12, and 2. That actually makes no sense. Well, that's clearly a mistake. But it should be a 3 by 3 cell here. No, wait, 3 by 2 cell. But average is basically 12 plus 20 plus 8 plus 12 divided by 4, I think. 32 divided by 4 is 8. The sum of that divided by, yeah, so this should be 112 and this should be a 25. So just ignore that. That's the maximum of these. And then the average here is, well, is it 43, 37, 41, 69, 81? Nah, something's wrong here. But ignore these. Basically, you take the matrix and then you slide them. So let's say a 2 by 2 matrix. You slide them like this. And then the max here is 30 and the max here is 30 again. Then you do this. The max here is 70. The max here is also 70. The max here is 37. The max here is 112. The max here is 100. The max here is 25. So similarly, you do it for the average. You obtain a 3 by 3 matrix. Ignore this. Flattening converts the 2D array into a linear vector. So this part does the extraction, this part does the flattening. Then you have the classification in FCN. So recurrent neural networks. So ANN for sequence or time series data is very useless. So RNN comes into play there. So you have feed forward networks, you have a hidden layer and memory to remember sequence info, same weights everywhere, error propagates, you need part info. Why is this different from ANN? ANN can't handle sequential data, it only looks at the current input, cannot memorize previous inputs, it doesn't have any loops, it loses neighbor information. So this is why this is a common question, difference between ANN and RNN. So it's something to keep in mind. Performance metrics of classifier. So false positive, false negative, true negative are like some of the metrics. Accuracy is basically how many are correct. So precision is TP by TP plus FP. Recall is TP by TP plus FN. F1 score is 2 times precision times recall by precision plus recall. The final is confusion matrix, which is basically a matrix of the number of true positives, the number of false positives, the number of false negatives, the number of true negatives. This basically tells you how well the classifier is doing when you look at the matrix. So obviously a bunch of questions. So they've given this network, they've asked us to do get to the goal node by doing depth first search, breadth first search, and uniform cost search. Also depth limited search, also iterative depth search. This is the solution for that. Already explained um, in the previous video. Path cost, find path cost in heuristic function admissibility. This is an example for that. So you use greedy best first search. Then there's another question on DFS and DLS, IDFS as well. So some questions for module 3. So these are resolution questions. Um, the only type of questions you'll probably get from that module. So You practice these two, it should be enough. Just an important note here. If and appears in the negation of the goals, which is here, so let's say you end up with two statements for a goal, then you just add both as negation. So you add these two statements to the premise here. But yeah, if you read this question, you'll understand what I'm talking about. The next is module 6. So decision trees. So here you have to use a threshold for each age and income. So the global entropy, you have to find minus 5 by 9 log 2 5 by 9 minus 4 by 9 log 2 4 by 9. Just something to remember is log, if your calculator doesn't have log 2, then log 2 of x is log x by log 2. So you define a threshold, you split age into less than 32.5 by equal to by equals yes, income less than or equal to 45. So alternatively, what you want to do is, the principle here is you divide this table into different classes. So you take each column and then you find out the weighted entropy. So E of X, you've already known how to calculate. Then you subtract the weighted entropy sum from that. That is the gain that you get. So the column for which you get more gain. So let's say your age gain is zero point 0.5 and your income gain is 0.4. Then your parent node of the decision tree should be your age. The one with the higher gain should be age. So that then you write the same data set for income and by below here. And then if this class is pure, then you just make it a yes or no. This is a good thing because if you have like a bunch of values in greater than 30 and they're all yes, then you just put that as yes in a box. If not, then you repeat the process, you find the gain again, and then you find which part to actually get, and then you make another node and then you expand later. That's how the decision tree is made. Back propagation, we've already solved one of these questions, so it's fine. Hidden Markov. So the probability of a sequence of events where probability of current event is only influenced by the immediately previous event's probability. So this is irrelevant. The questions are more important. So consider a Markov chain with these three transition states, and this matrix. So the state transition diagram comes from this matrix, right? So if your A11 is 0.5, it means that the cost to go from S1 to S1 is 0.5. If this is 0, then this is A2, 2. So the cost from S state 2 to state 2 is 0. This means state 2 to state 3 is 0.66. So that's how you start draw a state diagram. So the probability here again is just normal probability of x1 given 3, probability of x2 um, equals to given x1 is equal to 3. Basically, you're asked to find probability. You're given here that the probability of x1 is x1 being 1 is equal to the probability of x2 being 2 is 0.25. Now they wanted to find the probability of x1 equals 3 and then x2 equals 2, x3 equals 1. But we know that from the Markov definition, this only depends on the previous state, which means we have probability of x1 being 3 to be 0.5 because this sums up to 0.5, 0.25 plus 0.25, which means the only remaining value is 3. So the only other state x can assume is 3, and that's a 0.5 probability. And then the probability of x2 being 2, given that x1 is 3, which means going from state 3 to state 2 is 0.5. Probability of going from state 1 to state 2 is probability 2, 1, which both you get from the matrix, and then you're able to evaluate that. Basically, Markov principle is a person's state changes gradually over time. And the second is emissions. That is, observation only depends on current hidden states. So we arrive at this. So probability of hidden states, comma observations is equals probability of S1, probability of O1 given S1, and then another product term, probability of ST, probability of ST minus 1, probability of OT, ST. So T is an instant in time. So an example is probability of S1, S2, O1, O2 is probability of S1, probability of O1 given S1, probability of S2 given S1 because it's T minus 1, probability of O2 given S2. So there's an example here. Initially, you're given two um, sets, right? One is a transition probability network and one is an emission probability network. You're also given some initial state probabilities. You're given a set of observations, you're given a set of classifiers. So they've told you that when states are SH, HS, the sequence that you get is frequent, non-frequent, non-frequent, frequent. So these are observations and these are your states. So SHSS is your S, FN and F is your O, and well, we applied this formula to this P of S, P of F given S, P of S 2H because H comes after S, P of N given H because that is our second O, and then probability of H to H because we're going from H to H, and then probability of N given N because N is going from N to N. And then next will be probability of S given H times probability of F given N. So you basically multiply all of those and you get 0.0044. That is for Markov. The final thing is maximum expected utility. So you have decision node, you have chance variables, and you have utility. You're given this table, you're asked to find maximum expected utility of B, B bar, and value of information. You're given probability of A is 0.8, probability of B given A is 0.4, probability of B given A bar is 0.5. First thing you do is find the utility of the decision when there is no new information. So probability, the utility of a decision is the summation of A over utility times probability. So this is A and A bar. Then you multiply that, you already have these values. Similarly, you do it for decision. So you take these values from this table and then you multiply it again and you get these values. And since there's no new information, the maximum expected value is of utility is 52 here and it's D bar. So now when you have new information, which is probability of B, then you want to illustrate probability of B in terms of probability of A. So probability of B is equal to probability of B given A times probability of A. We already know this. Plus probability of B given not A, probability of not A, which is 0.42. Probability of A given B is 0.76. Probability of A given not B is 0.82. This by base. So probability of D given B, which is, sorry, the expected utility, which is new information, is the same as before, but now P of A is replaced by P of A given B because B is new information. So it's the same formula. So you repeat this essentially. So this is U of A comma D, probability of A given B plus U of A bar D, probability of A bar given B. And then you repeat the same for expected utility of bar D bar with new information, which is 50.47, which gives you the greater value here. So your maximum expected utility is 50.47. The action that you have to take is D bar because that is the action that leads to the most value. The value of information is MEU new minus MEU old, which is 50.47 minus whatever the max value here was, 52. So that gives you 1.52. So yeah, that's all.